Hello, and thank you for joining us today for From Data to Insights: How Hyperspectral and Multispectral Imaging Transforms Industries, hosted by Computar Optics. Please turn off your video to preserve bandwidth. We also ask that you keep yourself muted during the presentation. Also, please hold your questions until the end and open the chat box and use the chat function to ask your questions. Jonathan, would you like to begin?
Yeah, thank you, Nina. Good afternoon, everyone, and thank you for joining us today. I'm excited to talk with you about hyperspectral and multispectral imaging and how they're transforming industrial and machine vision applications, and more importantly, how optics play a critical role in turning raw spectral data into usable insights. Today, we'll cover some imaging fundamentals, walk through system components and best practices, and then focus on one of the biggest challenges facing modern wide spectrum imaging systems, maintaining image quality across an unprecedented wavelength range. But before before we get started, a quick intro. My name is Jonathan Hackney. I've spent over 17 years working in industrial automation and machine vision, helping customers solve real-world inspection and imaging challenges. I hold a Bachelor of Science degree in industrial engineering from Texas Tech University, and today I support customers across the Western region by helping them select the right optical solutions for demanding applications. Some more about Computar and the CBC Group. For more than 50 years, Computar Optics, which is part of the CBC Group, has been a global leader in designing and manufacturing precision optics. We specialize in engineered lenses for industrial, scientific, and machine vision applications with a strong focus on optical performance, consistency, and reliability. Our goal is simple: to provide optics that allow imaging systems to perform at their absolute best, regardless of wavelength, environment, or application. Before we go any further, let's level set with some imaging basics. First, hyperspectral imaging captures a very wide spectrum of light and divides it into hundreds of narrow spectral bands. This provides extremely detailed information about the composition of materials and objects, well beyond what the human eye can see. Multispectral imaging, on the other hand, captures images at a smaller number of broader wavelength bands. It still spans visible and near infrared and infrared regions, but with lower spectrum resolution. This makes it faster and more cost effective for many industrial applications. And finally, SWIR imaging, or shortwave infrared imaging, typically operates between 1,000 to 2,500 nanometers. SWIR is particularly powerful because it reveals features such as moisture content, material difference, and defects that aren't visible in the visible spectrum. So when we think about these technologies together, the key takeaway is that spectral imaging is not just about capturing pictures; it's about extracting meaningful data from the light that we normally can't see. And that capability demands heavily on how well components in the system is matched to wavelength ranges being used. A machine vision system designed for SWIR spectral imaging typically consists of several critical components. So, when building a successful spectral imaging system, the most cost effective approach is to work methodically. First, clearly define the spectrum. That matters for your application. More wavelengths are not always better. Secondly, illuminate correctly. Without proper illumination, even the best sensors and lenses will underperform. Third, match your lenses to your sensor, not just mechanically, but optically. Consider pixel size, sensor format, and wavelength range. And finally, consider the entire system. True performance comes from optimizing how all components work together, not from focusing on a single part in isolation. Historically, capturing both visible light and shortwave infrared required two complete separate imaging systems. One system for visible light, another for SWIR, each with its own camera, lens, and alignment requirements. This increases system size, weight, power consumption, and cost, and it added significant complexity to integration and maintenance. The result was often an inefficient workflow and comprised performance in critical machine vision, inspection, and surveillance applications. Today, new sensor technologies are changing that landscape. A single sensor can now detect wavelengths from roughly 400 nanometers all the way to 1700 nanometers. However, while the sensor can see this entire range, a conventional lens cannot focus all those wavelengths at the same time. This is due to the chromatic aberration. Different wavelengths of light bend differently as they pass through glass, causing them to focus at different distances. The result is significant focus shift. An image that appears sharp in the visible spectrum becomes blurry in the SWIR range, and vice versa. Without proper correction, this completely negates the advantages of wide spectrum sensors. This graph illustrates the issue clearly. The black curve shows a conventional SWIR lens where focus shifts significantly across wavelengths. The red curve represents a VisSWIR Hyper APO lens, where focus shift is essentially eliminated across the full spectrum. This is the difference between comprised data and true simultaneous visible and SWIR imaging. Nearly across every industry, subtle material differences, hidden defects, and environmental conditions have a direct impact on yield, quality, and cost. Traditional machine vision systems see roughly what the human eye sees. And while that's been effective for many applications, the most critical information is often invisible in the visible spectrum. Whether it's internal defects, material composition, moisture content, or subsurface damage, the data you can't see is often the data that matters the most. This is where spectral imaging comes into play. Spectral imaging captures a small number of discrete wavelength bands, allowing us to differentiate materials that appear identical in visible light. Hyperspectral imaging takes this a step further, capturing hundreds of narrowband spectral bands. This enables extremely detailed material analysis and classification. Together, these techniques allow us to collect information across the visible, near infrared, and shortwave infrared portions of the spectrum, far beyond human vision. So just to ground us, the visible spectrum ranges roughly from 380 to 750 nanometers. Beyond that is near infrared. The further still is short infrared, or SWIR, which extends out to about 2500 nanometers. SWIR wavelengths are particularly powerful because they reveal information related to chemical composition, moisture, and internal structure, things that simply don't appear in visible light. When you find a single vision plus SWIR sensor with the right optical design, entirely new applications become practical. Instead of multiple cameras and complex alignment, you can capture visible and SWIR data simultaneously through a single optical path. This signifies system design, reduces cost and size, and enables applications that are previously impractical or impossible. Now that we've covered the fundamentals, let's look at what this actually enables in real world applications. Silicon is opaque in the visible spectrum, which makes it impossible to see internal particles or alignment errors between bonded layers using standard cameras. However, silicon becomes transparent at wavelengths longer than about 1100 nanometers, right in the SWIR range. By using an in-gas sensor and SWIR optimized optics, we can now see through the silicon and detect internal defects that would otherwise go unnoticed. This capability is critical for semiconductor inspection and yield improvement. In recycling applications, many plastics like PET and PVC appear visibly identical. In visible light, mechanical sorting is difficult and often inaccurate. SWIR imaging, however, can instantly identify material composition based on spectral response. Using this approach, recycling facilities have achieved sorting efficiencies as high as 98%, drastically improving throughput and material purity. In food inspection, surface appearance can be misleading. An apple might look perfect in visible light, while internal bruising or spoilage has already begun. SWIR imaging reveals subsurface defects early, enabling automated quality grading, early spoilage detection, and forward object identification. This helps reduce waste while improving food safety and consistency. Atmospheric conditions like haze, fog, smoke scatter, visible light, and severely limited imaging range, SWIR wavelengths are far less affected by these conditions. As a result, SWIR imaging can deliver clear imagery at distances to 11 to 20 kilometers where visible cameras fail. This application makes SWIR identical for long range surveillance and monitoring applications. Selecting the right lens starts with understanding the application. Key considerations including sensor size, pixel size, working distance, field of view, environmental conditions, and lighting. The lens must be chosen as part of the system, not as an afterthought. This checklist summarizes the key parameters to evaluate: matching the lens to the sensor and application, ensuring optical performance, and avoids costly redesign later. Modern sensors can now capture an extremely wide spectral range, often from about 400 to 1700 nanometers. The challenge is chromatic aberration. A standard lens focuses different wavelengths at different points along the optical axis. With such a wide wavelength range, this focus shift becomes severe. If visible light is in focus, SWIR is blurry, and vice versa. To truly leverage a broadband sensor, the lens must maintain a single focus plane across the entire visible to spectrum, visible to SWIR spectrum. The VisSWIR Hyper APO series was engineered specifically to solve this problem. It's true, apochromatic correction minimizes chromatic aberration across the entire 400 to 1700 nanometer range. A floating optical design further reduces focus shift across working distances. These lenses are optimized for modern high resolution sensors, including devices like the Sony IMX992 and the IMX993, which with pixel sizes as small as 3.4 micron. The VisSWIR family includes multiple solutions. The Hyper APO series delivers maximum performance for multispectral and hyperspectral imaging. The Hyper APO series, the VisSWIR Lite series provides a cost-effective option for high transmission across the visible to SWIR spectrum, and the reflex zoom lens supports extreme long distance observation applications. The VisSphere series has been recognized by leading industrial organizations for its innovation and performance. This recognition reflects not just optical quality, but real world impact across machine vision applications. So this kind of concludes the presentation portion of today's webinar. Thank you for your time and attention. I'd be happy to answer your questions. If you would type them in the chat, and we could try to get them answered for you guys.
Jonathan, we have one question here. What companies that you know offer a sensor which covers 400 to 1700 nanometers?
Yeah, there are several companies out there, and several well-known and not so well-known. I know that just off the top of my head, FLIR and those guys, they definitely have something. There are plenty of other SWIR. If you look up for just SWIR cameras, you'd be able to find some of the manufacturers. Some of the ones that I work with, Rosanen is pretty good, but FLIR is pretty good. There are plenty of other companies, even like Omron, that have come out with their own SWIR camera. So definitely check some of those out.
That's the only question I see so far.
Gotcha. Well, I appreciate it. If you're working with the other thing is, if you're working for, have a lens application or a project, definitely come by and check out our booth at the Photonics West Show in San Francisco. Our booth is 1569, and we can show you guys a couple of sensors there as well, or a couple of lenses, and I might have a camera as well we can show off. But if you guys are working on any kind of vision or veer plus SWIR applications, our team is ready to help, help you guys design the right type of optical solution. So feel free to reach out to us. You can shoot me an email, go to our website, or scan the QR code here.